Welcome to the fourth lecture on advanced mechanics. Today we talk equilibrium principle and fundamental laws. We're going to go through concepts of conservation of mass, momentum, and energy, and isotropic and anisotropic material. And also you're going to see equations for continuity equation, equation of motion, energy equations, and Hooke's law. Let's start with conservation of mass and continuity equation. We're talking about fundamental laws governing material bodies in a continuum mechanics. These laws helps us form systems of field equations, which must be satisfied at all points within a body. These equations dictate the behavior of the material under certain loading conditions. Same as before, we're gonna have help from Mr. Potato and the Pepper family. Here is an example application. We can use the concepts being taught in this lecture for example, simple modeling of SACCULAR aneurysm. This is the case that basically blood vessels balloons out, causing pressure to surrounding tissue. We can simply model that as a sphere under internal pressure due to blood and experiencing outside pressure being exerted to the tissue, and calculate the deformation, a strain, and a stress induced in that region. Let's see how we do it. Let's start with the concept of mass. Mass m is a non-negative scalar that measures the body inertia, basically tendency to resist a change in motion. Density that we show by rho as a function of x, current state, or p as a function of capital X, reference state, is a scalar field which is basically limits of delta m over delta v, mass divided by the volume, as the volume approaches zero. Rho is the density field in the current or deformed frame. V is the body volume in the current frame, and P is the density in reference or undeformed frame. V0 is the body volume in the reference frame. The body mass becomes integral of P dV0 over V0, or integral of rho dV over V. Before we continue, we need to know about the concept of material derivatives. The material derivative of A, and A can be any arbitrary tensor, any property of the material, for a particle group is basically the temporal rate or time derivative of change of A for that particle group. Assume we have a deformation from the reference to the current state, and we want to know the time variation of a property between these two configurations. So in material coordinates, it's simply partial temporal rate. So let's say the property A is described as a function of reference or undeformed state. So time derivative of A is basically partial A partial T. But in spatial coordinates, assuming that A is defined in the current as a function of the current states, it is the sum of local temporal rate at position x and the convective rate of change resulting from the particle spatial movement x dot. So basically, if A is defined as a function of x, the current state, the time derivative of A is partial A partial t. So the time derivative of the property itself plus partial A partial xk ddt of xk, which is vk. Basically, the property multiply the property derivative with respect to one of the states multiplied by the time derivative of that state. This part is called the convective terms. In coordinate free form, for Cartesian coordinate, of course, we get ddt is equal to partial partial t plus vk partial partial xk, or ddt is equal to partial partial t plus v dot the gradient of the property. Expanding this term, we have v1 partial partial x1 plus v2 partial partial x2 plus v3 partial partial x3. It basically says the time variation of any property expressed as a function of current states becomes the time derivative of the property itself plus the variation of the property with respect to each of the states multiplied by the time derivative of that state. Let's see an example. It says the temperature field in a continuum is given by the expression theta is equal exponential of minus 3t over x squared, and x squared is basically x1 squared plus x2 squared plus x3 squared, and x1, x2, x3 are current states. The velocity field of the medium is given as v1 equal to x2 plus 2x3, v2 equal to x3 minus x1, and v3 equal to x1 plus 3x2. It asks for the material derivative of theta, d theta over dt. So we know that d theta dt is partial theta partial t plus vi partial theta partial xi. The time derivative of the states multiplied by the variation of theta with respect to that state becomes equal to partial theta partial t plus v1 partial theta partial x1 plus v2 partial theta partial x2 plus v3 partial theta partial x3. So partial theta partial t becomes minus 3 e to the power of minus 3t divided by x2. For v1 partial theta partial x1, we have x2 plus 2x3 multiplied by partial theta partial x1, which becomes minus 2x multiplied by 2x1 multiplied by e to the power of minus 3t divided by x to the power of 4. And the same for V2 partial theta partial x2 and V3 partial theta partial x3. So replacing these 4 into the relation for material derivative of theta, and simplifying it, we get d theta dt is equal to 3x squared plus 6x1 x3 plus 8x2 x3 multiplied by minus e to the power of minus 3t divided by x4. Conservation of mass. Conservation of mass says the body mass is invariant. Basically, it doesn't change or remain constant under motion or deformation. So basically, the time derivative of m should be 0. Let's substitute dv with j dv0, where j is determinant of f, the deformation gradient. And we already know that fij is xi comma j. For example, f12 is partial x1 over partial x2. x1 is current frame and x2 capital is the reference frame. We basically get m dot equal to d over dt integral of rho j dv0, and if we input d over dt, we get integral of rho dot j plus rho j dot dv0 equal to 0. For j dot, we can have j x dot I comma I, basically j divergence of x dot, which can be shown by nabla dot x dot. And for rho dot, which is basically d over dt of rho, we can write partial rho partial t plus partial rho partial xi xi dot. That's material derivative. For example, for the divergence of x dot, which is x dot I comma I, it is equal to partial x1 over partial x1 plus partial x2 over partial capital X2 plus partial x3 over partial capital X3. And for the term partial rho partial xi xi dot, if we expand it, we get partial rho partial x1 dot plus partial rho partial x2 dot plus partial rho partial x3 dot. Substituting these two for m dot, we get m dot equal to partial rho partial t plus partial rho partial xi dot plus rho x dot I comma I, j dv0. Know that x dot I comma I is divergence of x dot, and for the second two terms, we can write it as rho x dot I comma I. Expanding this differentiation, we get the same two terms as here, equal to 0. So simply, it gives us mass conservation equation. Basically, partial rho partial t plus rho x dot I comma I is 0. And if the material is incompressible, meaning that rho dot is 0, we can simply write x dot I comma I is 0, or divergence of x dot is 0. That's the conservation of mass equation. What about continuity equation? Continuity equation derives from conservation of mass, implying that the mass must be the same in both the reference and current configuration. So we don't get any change in the mass if the body deforms or moves around. We already know that mass is integral of rho dv or rho j dv0 over v0 or p dv0 over v0. So we can simply from this part of a relation write rho j is p. The density in the reference frame is j, which was the determinant of f, multiplied by the current density. Although the mass remains constant, the density may change. Taking a time derivative and considering that we already know p dot is 0, we get time derivative of rho j is equal to p dot, and we already know p dot is 0, so rho j is p, and the time derivative is 0. This is called the continuity equation. Here's an example. Let a body with fixed mass motion be given by x1 equal to capital X1 plus a t square capital X2. X2 is equal to capital X2 minus t2 capital X1, and X3 is equal to capital X3. Determine if the body is incompressible. So from the mass conservation, we can write the divergence of x as partial x1 partial capital X1 plus partial x2 partial capital X2 partial x3 partial capital X3. Partial x1 partial capital X1 is 1, partial x2 partial capital X2 is 1 again, and partial x3 partial capital X3 is 1 again, which equals to 3. It's not 0, so rho dot cannot be 0, so the material is compressible. Second part asks, deform the state volume of an element dv at time t equal to 1 second if reference or initial volume of the same element is 1 cubic meter. We already know that dv is equal to j dv0, and j is determinant of f, and we already know that f is the gradient of the deformation. We can simply derive f as 1 t square 0 minus t square 1 0 and 0 0 1. So the first term is basically partial x1 partial capital X1. The second term here is a partial x1 partial capital X2. Replacing t with 1, we get 1 1 0 minus 1 1 0 and 0 0 1. So j is the determinant of f, and I've already calculated that to be 2. So simply dv, the current volume, is twice the initial volume. Initial volume was 1 cubic meter, so the current volume is 2 cubic meter. The third part of the question asks, deform the state density rho if reference density is P equal to 6,000 kilogram over cubic meter. We already know from continuity equation that rho j is P, so rho becomes P divided by j, so basically rho is half of P, equal to 3,000 kilogram per cubic meter. Here's another example equation, but I leave it as activity for you to be done before the next part of this lecture. It asks if you can prove that dv is equal to j dv0. It is called Nonson's relation, and you should basically show that j is determinant of f and satisfying this relation. As a hint, you can start with the definition of dv and dv0 based on x, the current dimensions, and capital X, the reference dimensions. Good luck.